What is the rank nullity theorem? Why is it important? So, in a certain sense, the statement is super simple. Number of columns of A, dimension of kernel of A, plus rank of A. Let's decompose. This statement has a very precise geometrical intuition that ladders on all the intuitions that we did up to now. First of all, if I have a transformation that is from R2 to R2, and I have that this one is the kernel, from the intuitions that we got yesterday, should be that all those points get mapped here. All those points get mapped somewhere. All those points get mapped somewhere, true? And in a certain sense, we have that all those lines go forming those points that are aligned there. True? Together? How much are we together on this, people? 1, 2, 3. Excellent. So now we start from R2 and we end up in R2. Rank of A. What has it to be? This is the dimension of the range. True? This is the dimension of the range. What is the dimension of the range now? 1. True? What is this one? Dimension of the kernel of A. This is the kernel. True? This is 1. Are we together that the number of columns of A is 2? Do you see? What is happening right now? We start from a certain fabric of space and we end up into a space, but actually the fabric is compressed along a line. True? We were having a kernel. The kernel was making us kind of lose one dimension. True? You see that the kernel is making us lose this dimension. All those points are an equivalence class. Every line here is an equivalence class in the sense that every point here goes into the same point there. True? So, in a certain sense, every point here is equivalent among each other. How much are you following me, people? 1, 2, 3. Perfect. Let's make another example. Now, we go from R3 into R2. R2. How is the dimensions of matrix A? What is the dimension of matrix A? Discuss. Question. The kernel is the set of points in the domain that go mapped into the origin of the codomain. Watch out if this one is not clear, you might be the stuff that we did yesterday. This stuff here that we did yesterday, this one has to be clear. Otherwise, this theorem here that is based on the rank on the kernel is not going to be clear. So you will have to recheck this stuff here. The kernel, what is the kernel? Anyway, the kernel in brief is all the points in the domain that go mapped into 0 in the codomain. It might be with some dimensions, it might be with no dimensions. Let's make another example. Okay, let's go back to this question first. Dimensions of matrix A. It starts with elements that are in 3 dimensions, and it ends up in elements that have 2 dimensions. So it has to be something that looks like this. True? 2 rows, 3 columns. How much are we together? Perfect. Can I have dimension of the kernel of A equals to 3? Yes, no, I do not know. If yes, find the example. Discuss. Hey, what am I writing? So what will you say, people? Somebody says yes, we can have it. Which matrix do we need? 0, 0, 0, 0, 0, 0. True? Together? Because every stuff three-dimensional here gets mapped into 0. Everything here gets mapped into this. How much are we together, people? Perfect. This one, in this case, equals to, with the fingers, 0. How many columns do we have? 2. Perfect. Are we together? Find me a matrix A for which the dimension of the kernel of A is equal to 2. Go. This, still this stuff here. Okay, go, discuss. Can it be this one? Definitely no. It's going to be very, very easy modifications of that one. It's going to give you a dimension of kernel equal to 2. Discuss. Anybody wants to propose something? What would you propose, people? Yeah, overly complicated. I think this one is going to be okay. True? Why? Because here, if I put 0 something something, I go to 0. True? Do you see it? You see, it's a simpler example. But let's do also the other one that is interesting. So let's start. Sorry. How do we represent the matrix A? It's going to be A1. True? This is A1. And A2, A3 are here. True? Together? For finding the kernel, how do we find the kernel? The kernel, where does it live? In the domain or the codomain? The domain. Perfect. What do? I plot the rows. True? And the first row is going to be T1 and T2 is 0. And then what do I need to find? How do I find the kernel? It's all the vectors that are in the domain that are orthogonal to the first row and the second row. But the second row is 0, so it's always orthogonal. That means all this plane here. True? And indeed, here it is. True? Dimension, kernel 2. True? Rank of A. What is the rank of A? If I start from 1, 0, 0, where do I end up? I end up in 1, 0, true? This is E1. E1 leads to A1, true? How much are we together? 1, 2, 3. This is always true. Always true. Now, if I end up here, if I take 3, I end up here, true, 3 times. If I put minus 0.7, I end up here, true? What is the range of A? The range of A is going to be this whole subspace. True? Are we together? This one equals to 1. This one equals to 3. You see? Perfect. You do the considerations now, all the considerations, also the graphical ones, with the example that somebody was proposing before. May you repeat me? Was like 1, 2, 2, 4, 3, 6. Yeah, this one. Go. Do the drawings here, and tell me this, this, and this. Okay, go. This is what happens at the exam. Okay. Okay, let's look at it together. We go from R3 to R2, true? Then we have A1, A2, A3. Look at me, people. Look at me. We have the matrix that goes from R3 to R2, true? And we have A1, A2, A3 in the codomain. A1, A2, A3, they are aligned, true? It means that the rank is 1 because the range is this one. Are we together that this is the range? 1, 2, 3. Perfect. Let's look at the kernel. How do we find the kernel? We put T1, T2. T1 is like 1, 2, 3. T2 is 1, 2, 4, 6. They are aligned. True? They point out. True? What is the kernel? The stuff that is orthogonal to this stuff here. That means this plane, green plane. True? Are we together? 1, 2, 3. It means that everything inside here gets mapped into here. And if I take something that is a plane that is shifted, this one goes somewhere here. If I take twice, I go here, etc., 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 depending on the matrix. I'm not doing them on scale, but you got the point. Are we together? This one, this one, two, this one, three. What is happening from a physical perspective? Whenever I've got a kernel of A, the kernel of A somehow eats away some dimensions. In which sense? If the kernel of A was having dimension 1, it means that we would have an equivalence class. Let's redraw it. I go from R3 to R2, and this is general. Now we will generalize. If I've got dimension kernel A1, it means that I've got lines that are equivalence classes. True? It means that in a certain sense, I'm eating away one dimension. True? Because it's like kind of I got one dimension that I'm compressing. True? How many dimensions were I starting from? I was starting from 3 dimensions. And I will end up in something. True? What is the max here? The max is the number of rows. True? In this case. Do you see it? What is happening? I start with some ingredients. Some dimensions are going to be eaten away. Some dimensions I'm going to be able to reach. Let's make an example. Let's see if you see that from. If you tell me if, ignore this for now, and you tell me from an intuitive perspective if this situation is possible. I have a kernel in the domain, I've got a domain R3, codomain R2, okay? I've got a kernel in the domain of dimension 1, and I've got a range in the codomain of dimension 1. Discuss if this is physically possible. What does it mean? Let me give you an intuition. This is the kernel. This goes inside here. True? Then I've got this line here. It's in 3 dimensions, okay? Think at spaghetti. You got the central spaghetto, and then you've got spaghetti all around in a volume, in 2 dimensions. True? You see? Every one is going to be one equivalence class. True? Can all the spaghetti around go like on a one-dimensional scale or the one-dimensional domain, codomain? Think about it. Think about it. Discuss about it. I want you to see. Okay, people. This is feasible, not at all. I do not know if it is feasible or not. It's not feasible. True. Why? Let's dissect this. This one has to go somewhere. This one that is somewhere else. This one cannot be computed as twice or 3 times this one. This one, in a certain sense, it's points that are not linear combinations of those points. True? True? That means that what I get from this one cannot be in this line. It has to be somewhere else. You see it? So I cannot have only one dimension. I need to have 2 dimensions because somehow the equivalence classes span 2 dimensions. There's a question. Is the same thing of saying that, for example, if you got a situation like this of the spaghetti and like this, they would be like plotted in the same point, because here, if you say, okay, I need to have this situation here, it means that all those spaghetti should kind of be aligned, and it's not feasible because somehow the kernel is one dimensional. Okay. Now let's I'm following. I'm completely lost, kind of. It means that there's some questions. If I see several tools, it means that there are some questions. I don't get why you can project the line into a one-dimensional. No, you cannot do that. Let's make an example. Let's make a numerical example. Let me construct it so that we are in a good shape. 1 0 0 1 0 0. In this case, we have T1, T2, kernel. Together? Together? Perfect. Then let's make the codomain. If I start from anything along here, where do I end up? Here. True? Perfect. If I start on this spaghetto that is aligned with basically E1, E2, E3, E1 in the domain. If I take the spaghetto that passes aligned, how do you say, parallel to the kernel, centered on the E1. Do you see that spaghetto, people? Perfect. This one, where does it go? This one is going to be 1, 0, 0. This one goes in A1. True? It goes here. Together? This spaghetto here, can it go lying here? No. True? It has to go to some place that is a different place. Do you see it? And indeed, this one goes here. You see? And now, if I take the spaghetto that is the combination of E1 and E2, okay, do you see it? It's basically this spaghetto here. Do you see it? Where will it go? You say. Superposition of the facts. Always superposition of the facts. So this spaghetto is this plus this. True? That means where I end up is going to be the sum of the effects. This is where I end up. How much are we together, people? 1, 2, 3. Okay. Step back. In a certain sense, are we together that whenever I've got a kernel, the dimension of the kernel is somehow eating away some dimensions because it's collapsing a subspace? And all the equivalence classes that are the translations of that subspace. How are we in very much together? Not at all, kind of. Perfect. We have, moreover, a codomain that is the maximum dimension that I can reach. True? Perfect. In a certain sense, look at this picture here. This picture here is working for generic dimensions. Okay. I start with a domain that has got some dimensions. Here, the domain is smaller than the codomain. Okay, but you can do it vice versa. It doesn't change. We have a domain with 4 dimensions. We have a certain kernel that eats away some dimensions. The dimensions that remain are going to be mapped into the range. Because if here I was having kind of the kernel, I was having something like this. The kernel eats away this dimension. That means all the points on those plane, on this plane, they are equivalence classes and they are kind of independent. How many dimensions, independent dimensions, do I have this at this point? 3 minus 1, that is basically because the kernel is eating away 1. Where do I end up? I end up with 2-dimensional stuff. If instead I was having that the kernel was eating away 2 dimensions, okay, the kernel was eating away 2 dimensions, what were the equivalence classes? Points along one line, true? Because all the equivalence classes are all planes, true? It means that I've got one line that is going to go into one line. Okay. How do we feel? Non-trivial stuff. How does it enter into automatic control topics? Range of this A equals to 1. True? The range is 1. True? Dimension of the kernel of this A. How is it to be? Discuss. I start with 2 and I end up with 2. True? I see that I'm losing one dimension. True? I start with 2. My codomain is 2, but actually the real codomain that is the range is only 1. This one, can it be 0? No. This has to be 1. True? Can the origin be asymptotically stable? Yes, no, I do not know. Asymptotically stable means convergent and marginally stable. People, what would you say if I've got range that is equal to 1, or better, the dimension of the rank of A is 1. True? The kernel has to have dimension 1, rank nullity theorem. The origin, can it be asymptotically stable? No, because this implies that there's a set. I do not know how. I didn't plot it, but I don't care about how to plot it. I know that there's a set of equilibria. True? If this is a set of equilibria because the kernel gives me the equilibria of the dynamical system autonomous, x dot is equal to ax, okay? Autonomous version. Can I find a delta such that starting from delta I will converge eventually to the origin? No, because I have always some equilibria here that if I start there, I will stay there forever. See? You see how the rank nullity theorem tells us directly, in a certain sense, the stability properties, or better, rules out some stability properties. That is the convergence one, in case we have rank deficiency. The matrix 1, 2, 3, 4, 0, 0, 0, 0, 2, 4, 6, 8, and 1, 1, 1, 1. Can I have the origin asymptotically stable? Yes, no, I do not know. I would say that if you don't see that this one is rank deficient, this is rank deficient for 2 reasons: 0 and this linearly. Actually, the range here is going to be 2. The dimension of the kernel is going to be 2. See it? Because dimension of the for square matrices, dimension of the kernel plus dimension of the range is equal to n. Okay. But in general, we might also have this rank nullity theorem for non-square matrices. Very much okay, not at all, kind of. Are there questions? I see some tools. So tools means questions. Yes.
Elaborate more on the part where you said you only have
You mean this one? So this one and this one, they are this the double of this one. True? Perfect. This one is 0. Perfect. If we were to plot it in 4 dimensions, we would have A1 and A2. A3. True? A2 0. A4 something like this. A4. True? The range is going to be all the linear combinations of this stuff here. True? There is a plane that has dimension 2. Rank nullity theorem, kernel dimension 2. How do I find the kernel? I plot this, and I find the orthogonal. Can those three live in a volume of dimension 3? No, they have to live in a space of dimension 2 because they have to define the kernel. Another question.
What did you say was the difference for square matrices and not square?
That you go somehow with dimensions that might bounce around. So the formulation in general is this one, is that somehow here it's the same. It's the same. Only that in a certain sense you do not have to think the fact of the dimension of starting and dimension of ending. It's the same, but somehow you can say that if you have n, you don't care about the number of rows or columns for a square matrix. You know that n is going to be this one. So you kind of drop remembering that this is the number of columns. Because this one actually requires a little bit more interpretation. That we saw. Okay. Okay, are we together?